So guys, now we are going to do a very simple exercise based on the Carnot steam cycle. So let us look at the properties of this Carnot cycle. Steam is supplied as dry saturated. Okay, dry saturated meaning saturated vapor. In the textbook, we refer as dry saturated. But previously, when we learned in thermodynamic, that also referred as saturated vapor. At a 40 bar to a turbine, and the condenser pressure is 0.04 bar. If the plant operates on the Carnot cycle, determine the thermal efficiency, the heat input, the net power output, and the specific steam consumption. So before we try to elaborate on the equation needed in order to solve for number 1 up to number 4, sorry guys, this should be as a number 4, not number 3. Typo. So let me correct that. So this is number 4. So let us look on the Carnot cycle sketch on the TS diagram. So now we have our TS diagram. Our saturation line, and then we have our two pressure, which one represent the pressure of boiler, high pressure, and another one represent the low pressure, which represent the condenser pressure. As we know that for a Carnot cycle, we are going to operate the cycle underneath the dome, which have the rectangular shape. So this is the rectangle which represent our Carnot cycle. So this is downward expansion process in turbine, isentropic expansion. So this is state 1, this is state 2. And then we have our heat rejected in the condenser, which represent the isothermal compression process, 2, 3. And then 3 to 4 is our compression process in the compressor, which represent as the reversible adiabatic compression. And lastly, it will be 4 to 1 is the heat supplied to the boiler as the isothermal reversible heat supply. So this is what we have. And if we take our properties right here, our boiler pressure here, sorry guys, this is on the TS diagram, okay? So meaning that the pressure will represent by this line. Okay, this is the pressure line. So this is our 40 bar. And then again, next pressure, this is our pressure sketch on the TS diagram. So this represents 0.04 bar. So this is known as the P set at the given 3 to 4 or 2 to 3. And as far as the temperature is concerned, so now we have this is as T2, which is equal to T3, and this is T1, which is equal to the T4. And how to get the T1 and T2? This is basically the T set. Okay, this is basically the T set. The T1 is T set at 40 bar, and the T2 is equivalent to the T set at 0.04 bar. Okay, so this is all the pressure, and as far as the temperature is concerned, this is where we can sketch and name all these 0.1, 0.2, 0.3 and 0.4. Same thing, we could also write in this case the isentropic compression and isentropic expansion having the same entropy. S1 is equal to S2 and the S3 is equal to S4. So what is our S1? Basically S1 is Sg at 40 bar. S1 equal to S2 is equal to Sg at 40 bar. While the S3 equal to S4, S3 equal to S4, which is equivalent to SF at the 40 bar. So basically, what is the S4 minus, okay, the S2 minus S4? Basically, the S2 minus S4 is the SFG. Okay, SFG at what? At the pressure of 40 bar. Okay, this is SFG. Okay, S1 minus S4 is equal to SFG. Okay, so this is what we can write, put on the TS diagram. Now to answer the first question, it's a very simple question, just to have a an idea of Carnot cycle. So to get this thermal efficiency, in this case is a Carnot cycle. So this is equivalent to 1 minus low temperature. Low temperature right now is T2 divided by the high temperature right now is T1. And please be careful, the T1 and T2 should be in the absolute temperature scale in Kelvin. So the T1 and also the T2 you must put in as Kelvin, the absolute temperature scale. And to get the heat input right here, number 2, to get the heat input, we are going to use the entropy change concept, which is the Q41, which is equal to the T1 S1 minus S4. Again, the T should be in Kelvin. So that's how you put the heat input. And then after that, we are going to have the net work output. So the net work output, we are not going to use the SFEE in terms of the enthalpy change. It is using the W net is equal to the W12 minus W34. But right here, we are going to get the W net in terms of the thermal efficiency. Okay, we have the thermal efficiency. Let me put that in the fundamental equation first, so we can see clearly. So the thermal efficiency in this case is for the Carnot cycle, which is equal to the W net divided by the Q in. So the Q in right here is Q41. So we have solved the thermal efficiency in part 1 and we have solved the Q in part 2. In this case, we are going to solve for the W net. So it's easier using this formula rather than using the difference in enthalpy, because if you are using difference in enthalpy, you need to resolve the H2 and the H3, which involving X2 and X3, which is quite cumbersome. Okay, so it's easier to use this formula. And for the last part is to get the SSC. So the SSC is basically, we are going to use the first equation, which involving the W net in terms of kilojoule over kilogram. So this is equivalent to 36 divided by the W net. So we will have this in terms of kilogram per kilowatt hour. So that's it, guys. This simple example using the Carnot steam cycle to look how to solve it. Right? If given the pressure of high pressure, which is the pressure of boiler, and given the low pressure, which is representing the pressure of condenser. So if involving Carnot cycle, we always sketch the Carnot cycle on TS diagram as what I have sketched here. Always a rectangle which dealing within the saturation line. Always saturated vapor, right, or dry saturated. Always wet steam or mixture, where the process of 1-2 isentropic reversible adiabatic expansion. Again, the 2-3 always isothermal, because it is a isothermal reversible isothermal compression, and 3-4 is isentropic in the compressor, which represent the reversible adiabatic compression. And then the 4-1 is in the boiler, which represent the isothermal reversible or reversible isothermal expansion. Due to that description or types of processes which represent the Carnot cycle, for a steam Carnot cycle, we can only do it within the saturation state. Okay, guys, so that's it, the understanding how to solve the Carnot cycle.